Can someone internal check that the stream is working correctly?
Yes, control R.
So for those of you joining online, hello, good afternoon. A few people will be joining. So we'll get started now. Of course, you're all here today for the graph theory workshop. I'm going to get up the slides. Is that audio doing?
Stream works, audio works.
Okay, good. Cool. Just keep the volume down, please. Don't want to hear it echo. We're good to go? Are we okay over there? Excellent. Excellent. Wonderful.
Pizza might be coming early.
Are we getting pizza or are we getting...
Pizza.
Okay.
It doesn't have diary.
Then this diagram is accurate. So we are getting pizza. Good. If you haven't signed the QR code, please do so now. We are ordering pizza later. That should come in the second half towards when we are wrapping up the presentation. So what is happening today? What is this workshop about? Who are we? And why should you care? So we're here from CPMSoc. We are interested in graph theory from the perspective of competitive mathematics. We are also interested from more or less a sort of pure math perspective, which motivates the the competitive math side. So who's presenting today? I'll be presenting the majority of the first sections. I helped to write the slides, but mainly it was the work of Kevin Shuvir, who wrote the slides, especially the first couple of sections. But unfortunately, a few of them could not make it today. Vi will be presenting the last section on matchings. I'll be presenting everything before that, basically. If you have any questions during this, please do ask. At the end, we'll have a worksheet for you to work through. But besides that, we'll just be working through the slides, trying to see what we can learn, what we can revise about, what you may have learned in your courses already, and where we can take graph theory from a pure math or competitive math perspective to kind of extend and reframe what we've seen in earlier courses. So this, you may get a bit lost in this workshop if you haven't seen graph theory to some extent before. The reason why we have this first section on revision is because roughly we'll be assuming that you've seen graph theory in a course equivalent in some way to Math 1081, so discrete math. But if not, you can still try to pick up what we're talking about. We'll introduce pretty much all the notation, but again, it's hard to absorb that if this is the first time you've seen it. And this also could be interesting if you've seen graph theory from a COMP2521 data structure and algorithms perspective. Okay, so why do we care about graphs? So for me, at least the way that I care about graphs is that if I'm given a problem that I can see myself doing a lot of competitive programming problems recently, I like to think of graphs because they give us a nicer way to visualize the complexity of a single problem, a more concrete way to put our hands on what's going on in our problems. So they have applications to try to look at what is going on in your complicated systems with something that can represent vertices and something that can represent relationships, such as friendships and trying to match up partners for, say, a dance or so forth. That is an example. So you can also think of road networks when you have weighted graphs. And they can also be related to problems where, as I mentioned, for weighted graphs, we have some sort of optimization. We're looking through trying to find the shortest path, or if you know of maximum flow algorithms, some sort of combinatorial structure where you're trying to optimize. An example is actually optimize some sort of matching or some sort of other complicated possibility going on. So in that way, graphs can be very combinatorial. We won't get too much into that today, so don't worry too much, but it'll be mentioned to some degree at the end. And then finally, they can help. You use them to help visualize your problems in a competitive mathematics and competitive programming structure. The idea is this notion of a reduction. If you have this system, you want to reduce your problem to something that looks like a structure, a theoretical structure that you've seen before, examples of which is your graphs. Different types of graphs, your bipartite graphs, and so forth. What is a graph? So we've seen graphs before. What is a graph? The way that we want you to think of a graph for the perspective today, for the scope of today, is a graph is a set of vertices and it's a collection of vertices and a collection of connections between vertices. So for any single pair of vertices UV, we will write, you may have seen like tuples before, U tuple V, U comma V, to say there's an edge from U to V. That was quite interesting. I won't draw a connection with V.
You need a black box, John, to help since we
That's fine. We can also write UV. The way that we typically do it today is UV. That's other conventions in literature that's used. Edges are sometimes called arcs. If you look into more international-based literature. But in any shape, you have some sort of way of characterizing connections between your set of vertices. Okay, so in this workshop or most of the scope of what we look at, we're concerned with simple graphs. So what does it mean to be a simple graph? Well, mainly that just means there's no complicated edges. We might as well assume that the important structure of a graph is really usually encapsulated between, is there an edge at all between two particular vertices? And we don't care about if there's multiple edges or if there's a subpoint. Why do we care about only simple graphs? Well, for instance, if you're dealing with a weighted graph that has multiple edges between any two vertices in the context of trying to find the shortest path, then all you'd ever use is the shortest weighted vertex, shortest weighted edge between those two vertices. So we have this idea that usually our problems reduce to just looking at a simple graph is what's important. You can have multi-graphs, which you can look at in theory, where you have multiple edges between the two vertices. We'll look at graphs that look like this, which are much easier to draw out, and they look a lot prettier. So again, even now we're looking at the case where we're trying to simplify what we are looking at, trying to simplify the structure of what our problem encapsulates. Okay, so types of graphs. To try and revise. I know graph theory is a lot of definitions, a lot of terminology, so you don't have to remember all of these, but for those that are important, we'll try to emphasize and hopefully try to help you revise on your knowledge and why we care about them. So first of all, we have a cycle of length n that we call Cn. So Cn, get a little bit color. Cn, let's look at C5. C5 is a collection of vertices that are connected in a cycle. Every vertex has exactly degree 2 in this way. So you can think about looping around the vertices. Every vertex has exactly degree 2 in that way. So we have this special type of graph. The reason why I mentioned exactly degree 2 is because we're trying to think about how we can characterize this graph. It has this special structure. One thing we care about is that you can loop around it in exactly one Hamiltonian path, and every edge has to be involved in that path. There's also the complete graph, which is important when we'll talk about cliques later today. So a complete graph is a graph on n vertices such that every single pair of vertices have a connection between them. So I'll do C5. So C5 will look something like this. Every single pair of vertices has a connection between them. C4 is a box. This. So these are important. If you think about intuitively, cliques, the first time you might have heard that word is in the context of friend groups. If you talk about the published movie Mean Girls, a clique is a collection of people that pairwise are friends of each other. So that's generalizing that notion. Trees are nice because they have no cycles, so a tree could look something like this. There's a lot of different trees on n vertices, so this is not meant to say that when you're looking at the class Tn, for any fixed n, there could be multiple trees, but a tree could look something like this. Tree. Okay. And it's a very specific one, but this is mentioned in 1081. Hypergraph with 2 to the n vertices, which we denote Qn, I believe that's meant to be subscript n, as in instead of capital N little n. The way that we can think about that is if we look at a binary string, so what 0, 1 to the n is, this is a string of length n. So for instance, we could have, this is 3, we have 0, 0, 1, including this vector. And if you know anything about what a concept called Hamming distance, which is the number of different bits in the string, what you would say is that there's an edge between two strings if the Hamming distance is exactly 1. So I could have 0, 1, 1 here, there's an edge between these two. But for another example where I have 0, 1, 0, 1, 1, 1, 0. There'll be an edge here, but not an edge between these two. Because what's different is the bits that okay, so some visualizations there. You have a look at, those are most of the ones I've drawn. Okay, so some graphs are directed, some are undirected. We also have bipartite graphs. These are actually very important graphs, at least to me, when I'm thinking algorithmically from a computer science perspective. Bipartite graphs are very, very important. You can run a lot of different algorithms on bipartite graphs. What do bipartite graphs look like? I always visualize them as a set of x and y. Formally, what you say is that x and y are independent sets, so there's no edges between the vertices in x and y, but there are edges between vertices in x, two vertices in y. Something that looks like this. Bipartite graphs are useful when you're talking about maximum flow, partitions between sets, two-dimensional matchings, and colorings. In particular, the one we'll talk about now, that'll come up in a question we'll do later, is a graph is bipartite if only if you can color the graph into two colors, let's say blue and red, such that no two vertices of the same color are adjacent to each other. So we'll say that again. You can think of it as you have here blue for x, red for y. No vertices that are blue are adjacent, no vertices that are red are adjacent. Okay, so for example, we could look at it like these two. Okay, so there's this link between this other very important problem on graphs, which is coloring. You can try to color your graphs with two different colors. There's that link between coloring and this property of bipartiteness when you're trying to two-color your graph. Okay, so let's then just have a look at the complete graph. One of the questions today in the worksheet will, I believe, involve KMN, which is the complete graph with n vertices on one side and n vertices on the other side. It has as many edges as possible. Remember, it's still a simple graph. So for every vertex in x, it has every vertex in y as its neighbor, as it is adjacent to it. We say adjacent as in there's an edge between them. So n, for each of the n vertices, n times n edges. Okay. Yeah, so we have pen vertex, which is a vertex connected by one edge. That's not too important to us. Another notion is the complement of a graph. So whenever we're showing a mathematical structure, it's sometimes useful to, instead of working in our direct problem, instead say, no, I don't like this graph, let's work in the complement. In fact, one of the questions later today that we have in the cliques section will be involving complements. Complements are usually important when you have this notion of cliques, because one example is that if we go to, I didn't use the wrong notation here. This is the complete graph of 4 vertices, complete graph of 5 vertices. If I look at the complement of the complete graph of 5 vertices, what that looks like is it's just 5 isolated vertices, which is what we call independent set. And so there's this kind of duality between having a clique, which is every vertex is connected to every other vertex, and what's called an independent set, which none of the vertices are connected to the other vertices. And so for an arbitrary graph, you meet somewhere in between where in total, the number of edges is the number of edges in the complete graph of n vertices, which in the case of 5 is 10. But each one has an edge when the other one doesn't. So to go back and forth between the original graph and the complement is useful sometimes. That's why we put it up. We can also think about subgraphs. So subgraphs give us this notion of, I have this type of structure in my graph. Maybe that's not too important to me. Maybe I only care about what does the interior of my graph look like. So if you go into a room, maybe you don't care about all the details on this room. Maybe you don't care about this phone, this microphone. Maybe I only care about that chair. And so if that chair is my subgraph, then that's what's important to me. I might have confused a few people when talking about chairs. But at least I got people to look at. Wonderful. So subgraphs, you're just taking a part of the graph saying that's important to me. There's also this notion of induced subgraph, so this can get a little technical. But intuitively, the induced subgraph is I take a subset of vertices. What is the graph when I just restrict the edges to those vertices? There is a bit of notation for this. We use those brackets, the square brackets. If I have a set S of vertices, and I just want to look at what is the graph restricted to those vertices, I write G restricted to S. That is notation that I do like. It's useful a lot of the time. Yes. Any questions so far? Interest? I've talked about a lot of intuition, I suppose. Did anyone have any questions? Okay, I do have a question for you then. So this first question is based off two pieces of notation we talked about before, two concepts we talked about before. Cn is the cycle of length n. Remember we had C5 here. 5 vertices, they are all in a cycle. We want to show that Cn cannot be bipartite when n is odd. Does anyone have any ideas of how we could do this? Yes, Neil?
Use a graph order.
Sure, yep. So we can think about it as graph coloring. What would our argument be?
So like to the normal top of that medium element, those systems of like will then have something but like black when you like half go white.
Yeah.
And so if you like distance then an arbitrary vertex white or black.
Yeah.
When we go back around to it, it's gonna end up being a different color to what you.
Correct, yes. So what Neil was explaining, well, I guess those people that couldn't quite hear online, if you think about constructively, you can, if your graph is bipartite, there's a very constructive way to color it. And if you can't end up with, say, contradiction, then you can tell it's not bipartite. The way that you can do that is take any arbitrary vertex, color that your favorite color. If that's red, color it red. Then you would say its neighbors, the vertices around it, have to be blue. Then you could keep going, the vertices around that have to be red. Eventually, you kind of propagate that outwards. And if you end up getting back to your original vertex, getting back to a vertex you've already colored and saying you want to color it a different color, then that's a contradiction. Specifically here, we're going to basically use that idea in a sort of inductive fashion. So this question really should have said n is greater than or equal to 3, because I guess trivially you can color one cycle, though I guess that's not really well defined. So yeah, cycles at least 3. Base case, we'll do this inductively. This should say C3, not K3. In C3, someone please write down these typos. In C3, you can just do it by cases. There's a finite number of cases to color that. Well, it doesn't happen. I guess there's only one up to swapping around the colors and swapping around the vertices, but you'll have to have 2 adjacent vertices of the same color. The idea is basically what Neil said. Inductively, we could say if we assume that we cannot color for an odd number, if we go to the next odd number, so 2k plus 3, and we say, okay, suppose that we did have a coloring for the sake of contradiction, then what we could do is, well, we would have to have along the cycle 2 vertices of different colors. If we remove those 2 vertices, then we would have to have a coloring of the smaller cycle necessarily, which is a contradiction, so we cannot. Okay, questions on this? Cool, thank you. Right, so in terms of combinatorial structures of graphs, one useful property when trying to deal with the number of, or reason about the number of edges and number of vertices is when you're given limited information or when you're working in a programming setting, when you want to work out the number of edges, the motivation for this is usually, say, for instance, with planar graphs, we want to work out the number of regions. So if we just have limited information about what the graph looks like locally, as in we just know what the neighborhood of every vertex is, we can work out the number of edges in total by what's called the handshaking lemma. So what this tells us is it's kind of a double counting argument. So the way that we do this is we would say if we sum up the degrees, so remember I should actually said degree is the number of edges, in other words, the number of other vertices. So say the size of the set of U in V such that U edges degree into at least how many edges go into V. Summing that up would say for every edge in our original graph, we would count that twice when we sum over the degrees. So we would sum up at one endpoint and at another endpoint. So if we had U and V here, this be included. This is in degree U. When we do our summation, this would be in degree V. So every edge is counted twice. This counting argument, very combinatorial argument. And so we have this problem. We'll use this as well in another problem later in a slightly different way. So yeah, we double count. Okay, so we have another problem. Actually, I did say we're going to use this in another problem later. I was not thinking of this one. I was actually thinking of another one. But we do have another. We do have this problem which uses it. We want to show Qn was the hypercube of size n. So remember that was this diagram here, which said that every vertex, two vertices are adjacent, where every vertex represents the bit string of length n, so zeros and ones. You leave as a vector of n different zeros and ones. We say that the vertices are adjacent if only if the number of bits that they differ by is exactly 1. So here, 0, 0, 1 differed by 0, 1, 0, 0, 1, 1, effectively 1 bit. We can use the previous slide to work with this graph in a very local way instead of trying to deal with everything all at once. The way that we'll do that is there's a lot of symmetry in this structure of this hypercube. We would say that for every single vertex, if we choose every single random vertex, we want to look at the summation that we spoke about on the previous slide of degree V. V is a vertex in the set of vertices. The degree of V would be, if we look at an example, we look at 0, 0, 1, 0. If we look at n is equal to 4, well, the number of vertices I can get to from that one, if I draw my edges, could be 1, 0, 1, 0. So what I'm going to try and do is just change only one of the bits. So we need to say all the vertices that are adjacent to this single vertex we're looking at are going to be the same vertex with 1 bit changed, 1 bit flipped. So there'll be 4, that's the degree of 0, 0, 1, 0, so you go 4. So in particular, we could claim that 4 is hypercube of size n, degree of V is equal to n. So we can think about flipping any of the bits. Let's say for all anything. And so if we sum this up, this will be n times the number of vertices and n times 2n. Notice that we have n minus 1 here. Well, we can deal with that because we're looking at 2 times the number of edges. So in particular, the number of edges is n times 2n over n. So 2n over 2 to the n minus 1. Okay. Questions, concerns?
And also to listen to the assume a base case and prove that assume that it is true for K and prove that it is true for K plus 1.
I think you could. So it would be more difficult. Base case, of course, is easy to work with. So the suggestion was, can we do this in vector instead? Yeah, I suppose one way you could try to visualize this hypercube is you could have going from n minus 1 to n is you make 2 copies because the number of vertices increases exponentially, you double them each time. You'd have 2 copies of the graph from n minus 1. You have the number of edges there, and then you have also, you'd say that's like the new bit. There would be exactly 2 to the n minus 1 new edges. So what does that turn out to be? 0, 1, 0. This would, you can think of as 0, 1, 0, 0, 1, 1. We're just changing that last bit. So it'd be this plus 2 to the n minus 1. I believe that checks out. Yeah, that gives you the same answer. I'm going to move on to the slides, but if you want to ask me about what I did there, you can ask later, but it does work out. Yes. Good question. Okay, so, right. We are looking at just trying to motivate how we frame isomorphism. So isomorphism, I hope, is something at least you've heard as a word before in the context of graph theory. We're going to frame it in a slightly different way. So we're going to, again, talk about isomorphism, which is this kind of generalization of looking at graphs very abstractly and very locally. What isomorphism will do is we'll frame it in the way that it's a preservation of the neighborhood of a vertex. So I accidentally actually said this word neighbor a lot of times when I was speaking earlier. What a neighborhood of a vertex is the set of all vertices that are adjacent to it. So in this diagram, which really makes me want to see the new Spider-Man movie, we have Spider-Man adjacent to Harry, Aunt May, and MJ. He's not adjacent to JJ, J. Jonah Jameson, because even though they're connected, there's no direct edge there. So the neighborhood includes Spider-Man, but it also includes the other 3. And so how do we frame isomorphism? So isomorphism is a more general mathematical concept. For our purposes today, the idea I want you to get is that what an isomorphism does is under a specific map from one object to another object, we're going from one graph to another graph. Let's draw it abstractly. Drawing that. What we are doing, I'll give you some time to try and absorb what's on that slide there. We're trying to absorb the structure of one graph. So it's going from X to Y. Here we're going to go from the vertices in one graph to the vertices of another graph. We're trying to say that the structure that we care about, what do we care about in graphs? Well, vertices are just some labels. We label vertices by numbers. When I'm coding, I label my vertices 1 to the size of the vertices because I have 1 index, not 0 index. And so you can relabel the vertices, but what we want to preserve is what we care about in the graph. What the structure of the graph is the edges between vertices. And so in particular, what that looks like is saying that we preserve the neighborhoods of vertices. So we have this very local way of looking at it. So the neighborhood the neighborhood of any one vertex is preserved when we do this relabeling. So this is not to conflict with the way you may have been taught isomorphism. It's very, very similar. In fact, it's saying the same thing. As in every edge, if you have an edge between vertices in the original graph, when you apply v to it, you have u and v here. You have f of u and f of v here. Not u of n, sorry. You have an edge here. If you had an edge here, you get z here. That's actually 4 choice of notation. You would not have an edge here. So you don't want to choice. Okay, so it's a structure preserving map, preserving the neighborhoods. It's nice for us. For example, here, the idea is to say, okay, these graphs look different a bit visually, but 2 of them are actually really the same because the neighborhoods of every vertex if we kind of swiggle them around. If we look at y, if I kind of unfold one, then I can make it look very, very similar to the other two. 2, 4. Yeah, and you're kind of just move it around a bit more and release a bit more. Like the first one, Z is not going to be isomorphic to the other ones because one thing you could talk about is one part of what we would call an isomorphism invariant is that you have to have the degree sequence preserved. In this case, the degree sequence is not preserved. Okay. Right, so we're talking about planar graphs now. What a planar graph is a graph you can draw on a plane. I know, shocking. What does that mean? What does it mean to draw a graph on a plane? Well, a graph can be drawn on a plane if you can draw the edges between vertices such that the edges don't draw across. So, for example, you may have seen an example, which is the graph we saw on the previous slide. This graph, but not exactly the graph we saw on the previous slide. This is a graph that is planar. I wouldn't say it's a non-planar representation of it, but it is a planar graph. Because you can redraw it with that edge going around. So what we would say specifically non-planar graphs are graphs that we can never draw this planar representation. So why do I care about planar graphs? Well, for me, the reason why planar graphs is important, not that you need to know this, is that planar graphs can always be 4-colored, one of the two. Which is important to me from a computer science, theoretical computer science perspective, but for you, it's important because there's nice properties involving dual graphs. For a planar graph, what we can do is this type of duality operation, similar to taking the complement, but it's different. It is different. When we look at a planar graph, what we can think of is if no edges cross each other, then we can kind of non-ambiguously look at the regions made by this. So this could be one region, this could be 2, 3, 4. Do this things in a box. So the regions made by the graph on this plane that we're looking at. So one's the exterior and the others are the interior ones. We replace the regions with vertices and we replace the edges by edges going between the regions. So we have a good diagram here that illustrates what's going on. On the right, we are making this planar graph. We make a vertex for every single region. So we have this planar graph, as in we're specifically drawing it on a plane without any edges crossing. We are drawing edges. So there's an edge going through this edge in the original graph. So in particular, one thing you could observe is that the number of vertices in the planar graph, so in the dual graph, is equal to the number of vertices in the original graph. Forgive me if I mixed up the wording. And the number of edges is also the same. Any questions on this? So what do we, there's just, this note on the previous slide, the number of, construction, the number of vertices in our dual of our planar graph is equal to the number of regions, the number of faces in our original region. Some people call them face, some people call them regions. Where F is R is very funny because it's not in R there.
That words?
Oh, R is. Okay, sure. Okay, we'll work that out. Cool. Yeah. And as I said, the main reason why you care about planar graphs is you have this type of invariant where there's this relationship that's always fixed. So this magical number of 2 is equal to the number of vertices minus the number of edges plus the number of regions, which is something you have seen if you've done discrete math, and you can do a lot of things with it. For also planar graphs, you get this result that if you look at the degree of a region, so if you look at, let's look at region, I call this region A, I have some vertices going around it. The degree of this region would be 4. So the way I think about it is the number of stitches I need to cross over. I guess always thinking about flows and the number of ways you can escape the boundary, the number of posts, not the number of posts, but the number of fence lines along the fence around it. If you sum that up, then what you can observe is that for every region, every edge you cross over is counted once. So like with the handshaking lemma we looked at before, you get this new type of handshaking lemma for the number of edges, which is going to be useful for us. You also have Kuratowski's theorem that says, in a similar way to four coloring for planar graphs, has this result in terms of complete graphs and when we can and cannot, when we can or cannot have a planar graph. So specifically, we say that though we won't go into the detailed subdivision, one just like very simple image I'll draw for what a subdivision is that if I have three edges here, I could say a subdivision for this gives you just, I'll draw the other way, just removes a vertex in the middle. So through subdivisions, you can get in a non-planar graph a subgraph that's isomorphic to K33, the complete graph of three vertices on either side, or K5. So remember K33, I think you're comfortable with K5, but just remind you of K33. That looks something like this. It's a bipartite graph, three vertices on either side, like this, with every vertex included. Side like that. Okay. Right. And we do have some other results here. Do I want to go into the details? These are unrelated to Kuratowski's theorem. We're just putting Kuratowski's theorem there for reasons why you could care about cliques and also why you should care about planar graphs. But for connected planar graphs, you do have these other results, which you can prove by the handshaking lemma and by looking at Euler's identity for planar graphs. We'll leave that as an exercise for the reader, though, if you want to verify that. That is a good exercise because that has, in practice, shown up in examinations for discrete math. One thing that we will look at explicitly is going and showing that if you take the dual of a planar graph, the question you could ask is, when would the dual be itself a planar graph? And the answer to that question is, well, when the number of vertices of the original graph is equal to the number of regions of this planar graph. Yes, here. Yeah. So the way we can do that is looking at Euler's formula. So what we should have said, did we say it before? I intended for this to be indefinitely, but I think we still need to modify that, but they should say that a graph is planar if and only if, in fact, this statement is true. We should have that there. So we'll amend the slides. So what we would do is say that it's to show a graph is planar, it suffices to show that it satisfies Euler's criteria. In fact, if it doesn't satisfy Euler's criteria, this equation, then we are also found in classification. So what can we look at? We said from construction, the number of vertices that we get in our planar graph, we make one for each of the regions. So we know at the very least that the number of vertices of a planar graph is the number of regions to start off with. We're fine with that. And then we know from the handshaking lemma that the number of edges of our original graph is the sum over the degrees of each of the regions. So that'll be summing over each of the vertices and the edge degrees of the planar graphs. That's why we have this notion of the handshaking lemma for the kind of planar graph. It's important to us. So what that lets us conclude is that if we look at the handshaking lemma on each way, we can conclude that in fact it is true that the number of edges in our original graph and the number of edges in our dual graph for our planar graph are equal. And so since 2 equals 2, it's not since 2 equals 2, but by what we have found so far to be equal, we would have to have, I don't think this is like the best expression of what we're doing, but we are saying based off, well, what we know, if I want to write it out explicitly, what we know already is we have two equations. Sub it in, which I think it's not what's on there, actually. Yeah, so starting from the left side, we know that 2 is equal to vertices minus edges G. I'll just show the steps for that. It's not that bad. We know that the number of regions of our graph is the number of vertices of a complement. So look at the tool. And we just showed that the number of edges is the same as the number of edges in a dual. And we were working under the assumption, that's the part that's important, we're working on the assumption the number of vertices of our original graph is equal to the number of regions of our dual, which is helpful, so that gives us this other result here. Let's check. Let's check. Is there anything that we can say though about when this happens, as in when number of vertices of our original graph is equal to the number of regions of our complement? Is there a nice way to say that? Or does it just happen sometimes and not others? Exercise for the reader. I am curious though.
I mean, I hypothetically think you could make a case that this proves it like a very complex graph, even a complicated graph.
Well, I imagine, yeah, there are counterexamples. I'm thinking of connectivity though. One thing we do have to remember is that we're trying to apply this formula. What we should have said is that we're dealing with a connected graph. We do want to try to introduce this notion of our graph being connected, because Euler's formula as well only applies to connected graphs, connected planar graphs. So we have to keep that in mind as well. But I guess you can reason that if your original graph is connected, then your dual would also be connected by relatively simple logic. So we'll still have to think about that. But we'll get back to this. Okay, paths. I'll go through this very, very briefly, just to revise basically what you know about paths in 1081 or 2021. It's not 2021. Basically, what this slide is saying is that when dealing with Hamiltonian paths, well, what they are, first of all, is that it's a path that goes through every single vertex exactly once and repeats no vertices. What this slide is kind of trying to communicate is that, well, if you know a little bit about complexity theory and computer science, trying to determine if a graph has a Hamiltonian path is in fact NP complete, I mean it's very hard to find. If you want to have any hope at all of finding the path, basically what you have to do is brute force it. You can do it by recursion, but it's difficult. Are you trying to say something bad? Well, it's difficult. For Euler tours and trails, on the other hand, they're actually very doable. What you do actually when you want to determine if there is an Euler tour or trail, for that instead you're trying to have a for trail, you're trying to go on a walk that uses every single edge once. For tour, you allow the starting and ending vertex to be the same. And trail would have different endpoints. So you can look at the case of a trail that has a different starting and ending point. Basically, what you just look at is that there's these conditions on the parity of the degrees that lets you say, for instance, when you have every degree is even, then there's an Euler tour, and when exactly 2 of the degrees are odd, then there's an Euler trail. So trails are walks that don't repeat edges. Tours are walks that don't repeat edges, but that have the same starting in vertex. Okay. And quickly as well, we'll go over spanning trees. What a spanning tree is a subgraph of your graph that's a tree, basically, and it's spanning it. The reason why we call it spanning it is because we also need that subgraph to be connected. This is a very nice link between spanning tree is the maximally acyclic, and it's also minimally connected. And when we have costs associated to the edges, then we call a minimal spanning tree the spanning tree that has the minimum cost. There is this algorithm to work that out called Kruskal's algorithm. What you basically do in Kruskal's algorithm is you add edges iteratively. What I mean by iteratively is you go in increasing order of all the weights of the edges. And if you can add an edge without that causing a cycle, then you just add it to your existing tree. And when you're done, you would have a tree if the graph is connected. So you repeat doing. Okay. And yeah, we can also look at Dijkstra's algorithm. I'll just simply go through this as well. Dijkstra's algorithm also works on a weighted graph. This time it's trying to solve a different problem on a weighted graph involving paths called the single source shortest path problem, where what we are trying to do is given a source, which we typically denote as S, as we have there, we want to work out what is the shortest path from S to any other vertex. So the way that we visualize this is, or in the way that the algorithm works, is what we do for every vertex. We go from S, we kind of spread out from S. We spread out from S, looking at the vertices around it, and then around it again, in increasing distance away. So every vertex we visit would be the next vertex in terms of its distance from the starting vertex. So the next vertex we visit in this example, we'll start by visiting B because it's the shortest distance away. Then we visit A, then C, then D. So it's increasing. Increasing for like that. So the way I visualize it again is we go A's here, also A's here, then we have A here, and so forth. Okay. And yeah, the way you can recover your path is you keep track of the vertex you came from when you visit a vertex. So you can recover that from looking at the tree that you get by visiting the vertices. Okay. And in the case of the little caveat that T sees the terms and conditions of this algorithm is that you need to make sure all weights are non-negative. If weights can be negative, then you can use other algorithms such as Bellman-Ford. Okay. So yeah, sorry for this slide. These slides being pretty short. We don't have much to say. And unfortunately, let's look at what the main focuses of today. So we've looked at a bit of revision on what graphs are and how we work with them. We're going to have two special topics now, just to go briefly on cliques and then matchings. So I'll go to cliques and then hand it over to Via for matchings. So as I said, cliques give us this way to look at collections of people. So if you have, well, one result you can prove is that if you have 6 people at a party, where either people know each other or they don't, so either have an edge or they don't, what we can do is show that 3 people, there's either 3 people that are mutual friends or 3 people who are mutual strangers. This is a very important, very classical proof that's important to Ramsey theory. If you have questions about this, you can ask later, but have a go at it yourself if you want to think through the ideas. The hint is look at the complement graph and the original graph and look at a specific vertex. But what we're focusing on here is how do we approach this problem at all? So how do we put concepts to what do we mean by mutual groups? So the way that we do that is with a clique. So what a clique is a set of vertices that are such that every pair of vertices in the clique are connected. So in other words, a clique is a subgraph of your original graph that is a complete graph of the given size. So we talked about complete graphs before. They were this pretty type of graph here. And then we had 5 was this. So a clique is again this type of group of friends that all know each other. They're very, so think about clique, and then you could have this connected to other vertices like this in your original graph. Okay, so formally like this. So remember we said before, this means isomorphic. So it's isomorphic to this given size. If you have this induced graph, remember we talked about this notation, it's induced graph, the subgraph induced by this set of C vertices is isomorphic to the complete graph of the vertices. Remember, there's another reason why we care about isomorphism, because when we talk about cliques, we just said that they are KC. So they're saying something is something else in mathematical terms means this type of isomorphism. Having this clique is the same thing as saying you have a subgraph isomorphic to KC. So we can look at them in the same way. Okay, so cliques, when did we start caring about cliques? Well, any graph with an edge has a 2 clique, so that's not very interesting. What we start to care about is, and this is sometimes called an area of combinatorial graph theory called extreme graph theory, which is the study of how large or how small can my graphs be such that they do or don't have a specific property. What we're going to look at today is the triangle-free property. They call it this triangle-free, which means that there's no C3. There's no cycle of length 3. So there's going to be no subgraph that has a cycle. Okay. So we have a result on this. And for example, graphs that are C3 are cycles of length 4 or above. So a square is cycle 3. So you can still have cycles. So C3, triangle 3. A square is triangle 3. You get a lot of different complicated graphs that don't have any triangles, but as in they can have cycles, they can be, say, not trees, but they are still constrained with having no cycles. What we're going to be looking at here is something called Mantle's theorem. We'll look at the proof and we'll see the generalization of it, though we won't prove that generalization. So what is this saying? We are looking at a triangle-free graph with n vertices. What we claim is that the maximum amount of edges that it can have is n squared over 4. So remember, for a complete graph, if we're looking at kn, the number of edges was n times n minus 1 over 2. So we're saying what this roughly says is we can have at most a half of the number of edges of a complete graph of n vertices. So it is somewhat strong and somewhat weak bound in that way. And we're also claiming that equality only occurs when we have a bipartite graph. So if and only if, the same. We only have equality when we're dealing with this bipartite graph, where we partition the vertices into 2 halves and we draw every edge across either side. So looking at the proof of this, the idea for the proof is by induction. So there's other ways to prove it. We're just showing one method here. What we do inductively is say, we take our graph and we take 2 vertices that are connected to each other. We remove that edge, and then we use our inductive hypothesis, which is to say, okay, if I have this graph where there's no triangle in this graph, it's a triangle-free graph, and I remove one edge, let's say we take the vertices, we remove u and v, or we do more than just remove that edge, but we remove every edge involving those 2 vertices. If we remove all those edges, then what we're left is a triangle-free graph of n minus 2 vertices. And so what we have to have is that it's by what we're trying to prove, by induction. If we have 2 less vertices by induction, we would have at most n minus 2 squared over 4, because what we were claiming for 4 was at most n squared over 4. Here we've reduced n by 2. And so we just round up to ignore the 4 there. And so far we haven't really done anything interesting. We've just said so far that if we remove 2 vertices, which it is important that they are connected, but we remove 2 vertices, then the remaining graph can have at most n minus 2 squared over 4 edges. But then we actually use the fact that the graph is triangle-free. So what we want to use is that if we look at u and v, there's an edge between these. The claim that I'm going to make is that for any vertex A that's in other set of vertices, what we can observe is that we can have at most one edge from either U or V to A. So to write that down in words, you would say for all A in E without U will be the A, G, A, U. So let's say we cannot have both. A U in the edges and A B in the edges. Because if that did happen, then we'd have a triangle. Otherwise, we're not triangle free. So what we would try to do is say, every edge that doesn't involve U or V, when we count those up, we have n minus 2 squared over 4. Every other edge in the graph, well, we have one here, one edge here, and then we could have one for every other vertex in the graph, because every other vertex in the graph could be adjacent to at most one of U or V. And so in total, what we're able to do, what we've just claimed there, is we can sum up the number of remaining edges we could include, which would have to be n minus 1. So we could include every other of the n minus 2 vertices once, and then plus 1 for the original UV. And so in total, what we would have is the number of edges of this triangle free graph is less than or equal to the sum. I can reproduce that through because I'm pretty sure I still remember it. Let's just quickly look through this question. So we have lovely, after a number 670 participants. Thanks, Pat. In test one, what we're looking at is this condition. Let's try to translate this into graph theoretical terms. What we have is that we're going to try and draw edges between contestants if they competed against each other. What we know is that if we take any 3 contestants, at least one of them has competed against each other. So what that tells me is that if I look at kind of this complement graph of this structure, there are going to be no triangles because every 3 pairs of vertices in the complement graph, at least one edge is missing. So that's the idea we're trying to work towards. And so if Mantle gives us maximum value, then we could use this minimum value. Yeah. Okay, so we'll just briefly look through this. We're going to be looking at the complement graph. We're going to say by Mantle's theorem, in the complement graph, we have 2n vertices. So that means to say that the complement graph can have at most n squared vertices. So edges. So in our original graph, we have at least the total number of vertices in K2n, so edges in K2n, minus n squared. What that turns out to be if we use this result from a 4, so K2n, double that, that's n times 2n. What is that? Why is like this? Oh yes, and then we minus n squared. What's this? Yeah, n squared. So it's the same, yeah. So we get this result of n times n minus 1. And we would then say what we're trying to do in this problem originally, if we remember, let's go back, we're trying to find the minimum amount of matches that could have taken place, for this to be possible. So we would want this minimum, we're saying that the minimum cannot be lower than n times n minus 1, so that could be a good candidate. So let's try to see if it is possible for n times n minus 1. And we can see that we can construct this explicitly because this number is the same as 2 times n choose 2. So what we could do is split our participants into 2 groups and have a match between every pair in a group. Does that make sense? Okay. Yes. So the generalization then is when we're looking at having, instead of triangle 3, which was C3 free, if we're going to then say for a larger clique, C3 being K3, if we're looking at a larger clique, the number of edges in a graph without a clique of size R. Clique without, clique of size R plus 1, so we cannot have a clique of size R plus 1. Remember before we said we cannot have a clique of size 3. And so that would mean R was 2, so we get the 1 minus 1 over R was 1/2, as we saw before, was n squared over 4, consistent with this. The way that we can prove this is by induction. It's actually not too bad of a proof, using the same structure of proof if you understood from the previous part of Mantel's theorem. Full details in the if. But here, the way that you can get the graph itself that is maximizing the number of edges with this no k r plus 1 is use what's called a two-round graph, which is a kind of generalization of a bipartite graph. The details can be found, but you can prove this type of result, and it's looking roughly like the number of edges is this other way. Okay, I'll leave it to Via, and we'll just look at matchings now, and then we'll finish up today.
Thank you. Yep. Thanks. So, hope everyone's excited about matchings. We will be doing some actual matchings. But I guess to first begin, what is a matching? Well, a matching is basically a set of edges that don't share two endpoints and they're all matched together. So if you remember what Brendan did with the bipartite graph a while back, the best use for matchings is actually with a bipartite graph. So say I have this sort of bipartite graph. So the thing that actually happens with a matching is we essentially color certain edges that don't share the same endpoints. And those are our matchings. And that is the definition shown there above. So more formally, if you have two edges that obviously aren't the same two edges, the set of vertices of that edge must not share anything in common. Hence, the intersection is just the empty set. Yes. And if every vertex has an edge in the matching, then the matching is perfect. So that is an important property we'll talk about later. And now comes the other case. If you can't match every vertex, then the graph is M exposed. So that vertex is sort of exposed. It just doesn't have a matching. So over here, sure, you can match it. But say in this graph over here, you had one more vertex, like right here. You can't match this guy because if you were to sort of color in a matching, they would share the same endpoint. So you can't match this vertex. So this one would be an exposed matching. And another important thing is our matching is perfect if the number of M exposed vertices is 0. Basically, the graph is not M exposed. I mean, those were the fundamentals. Any questions at this point? Because we'll be getting into the intuition on the next slide. Yep. So, I mean, I'm not sure if people know X-Men, but we'll be explaining this scenario in terms of X-Men. If you see the above graph, it's all linking mutants together. However, we've colored in a matching between specific types of mutants. Mutants with claws that were in the first class and that were psychics. So in this case, this matching is perfect because if you look right there, each vertex is connected to the matching. The vertices colored orange are the matching. And just to illustrate another example of a perfect matching, we have this C4 right here. As you can see, if you put two of the edges in the matching, all the vertices are matched. So that is perfect. However, C3 or K3, I mean, can anyone do a perfect, matching of this? Anyone wanting to try? It would not be possible because if you try to put another one of these edges in the matching, they would share an endpoint, which would be very problematic. Thankfully, Brendan already has a very nice subgraph right here. If you look at this C3 or K3, you could treat red as the matching and these two as unmatched. And now we'll get to the meat of matchings, but before we do that, anyone have any questions on just matchings? Okay, that's good to know. So here's an important result. It's used a lot in competitive mathematics. It's called marriage theorem. Basically, if you have a bipartite graph, then any subset taken, I'll illustrate a diagram for better clarity. But just to keep things simple, this is our set X and this is our set Y. You have some vertices here and you have some vertices here. And this is a bipartite graph. I will illustrate with a complete bipartite graph. Yes, this is a bipartite graph. So in this bipartite graph, if you take a subset of this set X here, and this is the neighborhood, which is all the vertices adjacent to it. So you can think of this guy as Spider-Man, and this is MJ and Harry from Brendan's earlier example. So if you consider this scenario, then these are all the neighbors possible for X. Now, if you take a subset, Hall's theorem says that if there is a perfect matching, then the number of neighbors for our subset need to be greater than or equal to the actual elements in our subset. Now, in this case, yes, like if you take this as our subset, it has two neighbors right here. So it is greater or equal to, and this is a matching we can do. Yes. And this is a visual diagram on the slide. So over here, we do meet the conditions for our matching. As you can see, we can match everywhere. Over here, the condition fails because we can't match that vertex at the bottom. And something I hadn't pointed out before, this matching isn't perfect yet because we'll need to include this vertex to match out to here. Otherwise, this one is left unmatched. Basically, a nice analogy is every apprentice, treat X as your apprentice who wants an instructor, should have one. Like, you should be able to match them up, every apprentice having an instructor, or I'm not sure if people know this reference, but every Jedi apprentice having a Jedi master. That's all right. But yeah, now we shall get to the proof of it. We shall use strong induction for the proof. The reason we are using strong induction is because it allows us to look essentially backwards and try to prove it out. So first we must begin with our base case. If there is only one member in the set, like I'll draw a diagram right here. So if there is only one in the X, and then all you need to satisfy it is you should have one neighbor. If you have one neighbor and one X, that satisfies it. That is our base case. with applying Hall's condition. And then comes the inductive step. This one might need some visualizing, so I'll deliver a simplified graph. So consider this scenario. I mean, in general, there are n of them, so for now I'll draw in 3 vertices. But basically, the rationale is you assume it is true for this graph to have a perfect matching. You assume it is true right here. What we will be doing inductively is try to prove this is also true for any subset of x. Right now, we know it's true for all x. But let's say take a particular subset. And then we'll have to consider 2 cases for the neighbors of x. So one case is that a particular subset has more neighbors than the actual elements in that subset. In that case, we could still get a perfect matching if we just match it once, like right here, and remove the other one from consideration. So that is the first case. The extra buffer is simply there to ensure that Hall's condition is met. Like, once you do the matching completely, you'll have some unmatched ones, but you'll have some edges that aren't colored, but you'll have the vertices as perfectly matched. And then we shall look at case 2. Now, this, as I discussed at the start, is the trivial case. The subset has exactly n neighbors. So, just to give an oversimplification, let's just say there's 2 elements in x, 2 elements in y, and they have edges between them. Your trivial matching is basically just simply that. Nothing else to be concerned about. And this is only the forward direction. If you remember the actual Hall's theorem, it was a if and only if, right here. So we've just proven the forwards direction. The backwards direction is relatively simple to prove, but basically there would be a perfect matching because if you have so many vertices in the neighborhood, which remember are all adjacent to each other, you should be able to find edges that match everyone in X. So before we go to applications, any questions? Okay, I guess we shall move on to applications. Now, this is one of those very funny questions that doesn't look like you can apply graph theory. I shall also say SMMC had similar questions as well, and a worksheet will have similar questions too. So, anyone have any ideas on how we can use graph theory for this question? Remember that graphs are a way to model problems, as Brendan said. All right, so the way we can model this problem is we can actually consider 2 sets. So our X set can be all the rows, and our Y set can be all the columns. Now, if you read the problem, it says if a row and column intersect at a positive element, then the sum of their elements are the same. So what we can do is we can make edges between rows and columns that intersect. And since this problem only talked about the intersections of rows and columns, also trivially, you can't have 2 rows intersecting on a grid. Like, how would they intersect? It would have to be a row and a column. Our graph is bipartite, which means we can consider applying Hall's theorem. So that is the setup for how you would start to approach this problem. And our proof will basically rely on a proof by contradiction. So for a proof by contradiction, assume that without loss of generality, M is less than N. And we shall then try to prove this by strong induction. So our base case is when M or N is 1, it will have to hold because M and n cannot be 0. I mean, this is a grid. And now comes our inductive case. So we construct a bipartite graph, a lot like this one. We've labeled it C for columns and S for rows. And then what we'll do is basically, that is our setup like I've defined. Then what we'll do is, if we apply Paul's theorem, say we have C greater than or equal to S, which is basically n, which happens when n is greater than m. Yep. So if we have that by halves, then there should be essentially a perfect matching. No two of the same are in the same row or column. The underlying intuition behind this is, remember that we put an edge if that same positive element is there. If we have another one with the same row, we'll break the bipartiteness. What will happen is you'll have a matching like this. If it's the same one. So one thing I haven't explicitly mentioned is we're doing our matching when the positive element is the same. The edge actually happens when you have that positive element. And essentially, when that happens, then we need to think about what that actually means in terms of our grid. So if you go back, rectangular array, I mean specifically, but we basically need to consider what that means. So remember that it only contains at least one positive element. So if such a matching was to exist, what would happen is essentially the sum of the column entries would, sum of multiple column entries would be the sum of a row entry. And that would be problematic in the fact that it would imply some columns have zeros, which is how they originally approached this problem. And that is the contradiction, because if you go back, there should be at least one positive element. So you can't have a all zero column. And that is our contradiction. So we've then shown that our S has to be greater than C. Now, we need to do this the other way as well. I mean, it'll be very symmetric. And then eventually we'll reach the number of rows equals to the number of columns, hence m equals n. So that is a very straightforward setting. Any questions? There were a few typos earlier that we will fix, such as at the proof for halls, this is meant to be a subset Ek, not just a perfect subset. And yes. Thanks, Brendan. What it says. Yep.
If you haven't scanned the QR code yet, for those of you that came in a bit late, please do so now. This attendance form has escaped mine for the pizza you're about to eat, so please do scan the QR code. So thank you all for coming today. We'll let you eat pizza momentarily. We've given you a worksheet now. You can work through that. You can ask us questions about the slides, follow up on anything that you want to know. So yeah, thank you very much. We need to get a photo with the banner now so we can everyone.
I think that's the feedback form with those others.
This form is up at the top. There. That's the attendance form. Please sign this one. We'll get a photo with the banner now. So everyone just stay seated for the moment. Maybe Alex.
Sure. I'll get it back around.
Sure. That's fine.
Yeah.
The slides will be uploaded on our website, so if you have questions, queries, concerns, you can raise discourse on our discourse or otherwise. And the solutions to the worksheets will also be posted in about a week on the website as well, so please try to have a go at them before then. A few of them are quite difficult, but you can see the answers, you can assess the stuff. Yes, who's taking the photo?
I don't mind taking it. Are we standing?
Oh, we can just hold the banner in front of us.
Oh,
Can someone else hold the banner
Yeah, I can help.
on the other side?
Actually, not really.
Just like take it. Oh, sure.
Oh, like, yeah, that's fine.
Yeah, like.
Yeah.
Oh, get everyone in. Thank you.
Okay. Good.
Wait, where do I put the
Oh,
back?
I'll take the banner back.
It'll go out, right?
That's fine.
Oh, okay.
Just let everyone have food now.
Yeah. Please feel free to have food now. There is.
Oh, hold on, they cannot compete. They haven't done the event.
Cannot eat if you have not signed the attendance form.
I sign my soul.
You guys should advertise as well as other CPMSoc events we have coming up. Not that a lot of you, not that it'll be relevant to a lot of you, but we have a mock exam from 4128, COMP2521 next week on Tuesday. We have a session for MATH3611 next Wednesday. And we have a math talk tomorrow on information theory and combinatorics. Tomorrow from 11 to 1 if you want to join us there. So thank you everyone for coming. There's also a movie night on Friday.
Combined with your math.
After the math circle. The math circle starts from 3 p.m.
Yeah.
3 to 4 p.m. Yes. Math circles 3 to 4 p.m. Then the movie night is 4 to 6 p.m.
That's what I used to play. This was the highest you can get.
So you're enjoying Poco Chicken. We're getting
Cool.
We're getting sober for the movie night.
Yes, we are.
Yeah.
10:14.
PM?
You're going to be a fucking POI from again?
What's up?
I was ordering 20.
We are watching the Grand Budapest Hotel.
So, Pat, how does the pizza taste?
The speed is working.
Oh,
I have questions for you.
Dijkstra did that.
that's a fun one, maybe.
I have questions. When you true false theorem, you said the second case was easier when the all the same size.
Yeah, because then your like actual element is only just going to one.
Order it forward. Oh, I could have really seen it. It's just the same marketing with a paragraph at the end thing, really at the very end.
Yeah.
That's true. Like that's not true.
No, but like, if you're saying elements are like 2x, and then let's take up two elements and we're x, then
Like they could be connected. Same level.
yeah, you're right. It could actually be exposed. I mean, although when I was reading up the book for it, that's the rationale.
That happens. So like, you prove it doesn't happen.
Yes, you're right. It should ideally say each element has the same neighbor. Then yeah,
Like
you're right.
Like the drawing you drew, like that was assuming that
So that's taking one down for sense.
that case never happened. Well, that's nonsense.
Yes, I should have said an element. Yeah.
Wait, so you're first with like the columns and the rows thing, right?
Yes.
You were saying that. Actually, sorry. Does someone have a question here? Which they clean up the slides and also clean up the worksheets and the slides. You can look at the slides, but
Great source of dinner.
great stuff. Also, I should end the recording actually. That's a good place.
Be overweight from
Sorry, no, just take what you want. I'm not sure. You just cover Dijkstra's and Kruskal.
We did very briefly. I wouldn't use this as the best resource with that.
Doing the workshop.
That's right.
Exactly.
Yeah, so for those of you online, thanks for joining. We'll end the stream now. Come to other CPMSoc events. Yeah, the half section of the talk was a very big focus.